Hello students, today I'll be talking about the quantum mechanics. Before starting with the postulates and the equations of the quantum mechanics, let's discuss few important points about the basics of quantum mechanics. Okay, so the first thing I'll be talking about the difference between the classical mechanics and the quantum mechanics. Okay, so what is the classical mechanics? We all know that classical mechanics, it is formulated by Sir Isaac Newton in 17th century, and the macroscopic particles like the bigger bodies, these obey the laws of the classical mechanics. Okay, and the microscopic particles like electrons, protons, neutrons, these do not obey the Newtonian dynamics, but rather these obey the laws of the quantum mechanics or the wave mechanics. Wave mechanics is the another name for the quantum mechanics. Okay, so in quantum mechanics we'll also talk about the quantization of the angular momentum and the energy. And if I'll talk about the laws of the quantum mechanics, the laws of the quantum mechanics were formulated in 1925 by Born, W. Heisenberg, and P. Jordan, and the formulations given by these scientists, these are known as the matrix mechanics, and these are further advanced by the scientist E. Schrodinger in 1926. Another important thing about the formulations of the Schrodinger is that these are called as the non-relativistic quantum mechanics. Okay, these are known as the non-relativistic quantum mechanics, while the Dirac scientist, he formulated the relativistic quantum mechanics. So we have two types of mechanics: non-relativistic quantum mechanics, which was formulated by Schrodinger, and the relativistic quantum mechanics, which was formulated by the Dirac. Okay, now if I'll talk about the Newton's second law, I hope you people are aware of this, the laws of the Newton's. And the second law, it relates the force with the mass and acceleration, and the formula is force is equal to mass into acceleration. And in terms, if I express the acceleration in terms of velocity, then A is equal to dv by dt, that is rate of change of velocity, it is equal to acceleration. And if I further simplify the velocity with the displacement or the position, that is the rate of change of position, that is x, with time, that is velocity, and rate of change of velocity with time, it is the acceleration. So f, it can also be written as m d square x upon dt square, where x is the position of the particle. Okay, so in order to obtain the position x of the particle as a function of time, this equation, it has to be integrated twice with respect to time. And the first integration, it will yield dx upon dt, and second integration, it will yield x, that is position of the particle. Okay, and after each integration, there is our introduction of arbitrary integration constants, and these are the c1 and c2. Okay, these are c1 and c2. So in terms of the time and the c1 and c2, x can be written as x is equal to function of time c1 and c2, and f, as I told you, f is a function. Okay, and uh, now let's talk about the classical mechanics for a particle. If at a particular point of time t naught, the position is x naught and the speed is u naught. Okay, then c1 and c2 can be calculated from the equations. X naught is equal to function of t naught c1 c2, and same way the velocity u naught, it is function of f dash, that is f dash is the derivative of f dash t naught c1 c2. Okay, and um, and if we know, okay, so if we know the force f and the initial position and initial velocity of any particle, then as per the Newton's second law of motion, we can predict the position of the particle at any future time. Okay, so if we know the force, if we know the initial position, and if we know the initial velocity, then we can use the Newton's second law to predict the position of that particle at any future time. And this is for the one dimensional system. Even for the three dimensional system, which is having number of particles, we can predict their position, or we can predict with certainty their position at any future time. Okay, so we can say that in classical mechanics, the knowledge of the present state, it will help to predict the position of the classical mechanical system in the future. Okay, and that prediction will be with certainty, means the with accuracy we can predict in future about the position of that particle if we know the present positions of the particle. Okay, now if I talk about the quantum mechanics, now in quantum mechanics things are different. Okay, in how it is different, in classical mechanics we are predicting the future position of the particle with certainty, but in quantum mechanics we cannot predict the position of the particle with accuracy. Okay, and we can only tell about the probability. So quantum mechanics is about the probability of the future. Okay, and a reason is because in macroscopic bodies, bigger bodies I'm talking about, in bigger bodies, it is their velocity is very very less compared to the microscopic particles. Now microscopic particles are the electrons, the protons, the neutrons, and these are moving with the speed of light. Okay, and something which is moving with the speed of light, it is very difficult to predict its position and the momentum with 100% accuracy, and that forms the principle of Heisenberg's uncertainty principle. So we can say that in quantum mechanics we can only the quantum mechanics, it gives the only the probability of finding finding that particular particle at various locations in the space, while in classical mechanics we can talk about the position of the particle with accuracy, with precision. Okay, now in in quantum mechanics, the state of a system, it is represented or it is defined by a state function which is called psi. Psi is state function, it is called as state function, or it is also called as a wave function. Okay, so psi, which is the Greek word, okay, it is function of the coordinates. I hope you understand coordinates. These are the x, y and z coordinates, okay, of the particles of the system, and it is also function of time. So psi, which is the state function or the wave function in quantum mechanics, it is a function of coordinates of the particles and also a function of time. So it is dependent on both on the coordinates as well as the time. Okay, so let's talk about the wave function of a two particle system. Okay, so I am going to talk about the wave function of two particle system. Then the wave function of two particle system, it can be written as psi is equal to function x1 y1 z1, x2 y2 z2 and t. Now what are these x1 y1 z1? These are the coordinates of particle 1, because we are taking two particles, so I'll be talking about the coordinates of two particles. So x1 y1 z1, these are the coordinates of particle 1, and x2 y2 z2, these are the coordinates of the particle 2, and t, which I have written in the end, it is the time. Okay, so for a two particle system we can write the wave function like this. Okay, so this is the equation. Okay, now let's talk about the, now suppose we are having n particle system. Now we are not talking about two particle system, we are having n particle system. So for n particle system the time dependence psi can be written as, now we have n particles. These n particles, the number of n particles, it varies from 1 to n. Okay, so this psi, that is wave function for n particle system, it can be written as summation I is equal to 1 to n, means number of particles range from 1 to n, minus, this is your h bar. H, it is written and then a line is made on this. So h square, h bar square upon 2 mi, I'll talk about different terms involved here. Okay, into d square psi upon dxi square plus d square psi upon dy I square plus d square psi upon dzi square plus v xi vi zi psi is equal to I h bar d psi upon dt. It means your h square, h bar, it is the reduced Planck's constant, and its value, it is equal to h upon 2 pi. Mi is the mass of the particles, and of the all the particles. V is the potential energy again of all the particles, and I represents the number of particles here. Okay, so the above equation, this is known as the time dependent Schrodinger wave equation, and this equation is the quantum mechanical analog of Newton's second law. This is quantum mechanical analog of Newton's second law, and it was shown by a scientist that the classical limit of taking h is equal to 0, the time dependent Schrodinger wave equation becomes the Newton's second law. And the question that how the quantum mechanics and classical mechanics is different. The We can say that velocity of the macroscopic body or a bigger body is far less than the velocity of light. So microscopic bodies which are moving with the velocity of light, their velocity is very very large as compared to the velocity of macroscopic bodies. Okay, so in the end I would like to quote the statement of S. Hawking. He stated that the quantum mechanics allows us in principle to predict early everything around us within the limits set by the uncertainty principle. Okay, so in the end I would like to conclude this topic by saying that the classical mechanics, it is for macroscopic particles, the quantum mechanics, it is for the microscopic particles. There is a difference in the velocities of macroscopic particles and microscopic particles. Another thing is that the in classical mechanics we can talk about the future state of a particle with certainty, with precision, we can talk. But in case of quantum mechanics we can only there is only a probability of the future state, means with 100% accuracy, with 100% precision, the position of the particle in the future, it cannot be predicted by the quantum mechanics. Okay, so with this I end my lecture. Next time we will discuss the postulates of the quantum mechanics. Okay, so till then just concentrate on your studies and work hard. Okay, thank you.